It's really incredible to see how far LLMs have come, especially in the last few years. It's not just about generating text anymore. They're becoming agents capable of taking actions and interacting with the world. But as their ability to handle these like back and forth multi-turn interactions grows, you kind of hit this fundamental question. How do we make them truly collaborative partners, especially when dealing with really complex problems?
Yeah, you hit the nail on the head. It's not enough to just have them respond. We need them to reason, strategize, and truly work with us.
Exactly. And that brings us to what we're diving deep into today, this super interesting research paper.
It's called SWE-RL, Training Multi-Turn LLM Agents on Collaborative Reasoning Tasks.
Catchy title, right?
Right? And it comes from some pretty big names. Fair at Meta and UC Berkeley.
So the core idea they're tackling is, well, they're directly addressing a major roadblock in the field. How to train these LLMs to be truly effective partners in these intricate multi-turn collaborations. It's not just about improving performance by a few percentage points, they're really going after a foundational challenge. So for everyone listening, the goal of our deep dive today is to unpack how these researchers are pushing the boundaries of LLM training. We're focusing on the academic innovations, the really key breakthroughs they've made in teaching these models to collaborate effectively over multiple turns. And to do this, they've introduced a couple of very interesting things. A new benchmark they called Bench, and a really clever algorithm named SWE-RL.
Right, and to give you a sense of what we have to work with, we've got the paper itself, obviously. It goes pretty deep.
But yeah, dense, yeah.
Then there's a briefing document that kind of summarizes the key points, a timeline that lays out how the research progressed and who the major players are. Plus a study guide with quizzes and essay questions if you want to really test your understanding.
Yeah, definitely check those out if you want to go to full academic on this.
And to wrap it up, we've got a Q&A section that breaks down the main takeaways in a really simple way.
So a whole buffet of resources for you to dig into. Let's get started. The whole thing we got to talk about is Bench.
Bench, yeah. The paper really highlights this as their primary contribution, a new benchmark.
A benchmark built specifically for multi-turn RL research with LLM agents. So what was wrong with the existing benchmarks? What gap were they trying to fill here?
Well, they realized that existing benchmarks for AI collaboration weren't really cutting it. They lacked this crucial combination of features you need to really train sophisticated LLM agents. Like, many of them didn't have enough task diversity. For robust RL training, you need a lot of variation so the models don't just overfit to a narrow set of examples. Also, a lot of these benchmarks weren't complex enough to demand the kind of reasoning and generalization we're looking for. We want these LLMs to have to think deeply, not just learn simple patterns. And finally, a lot of them had a ton of engineering overhead, which slows down the pace of research. You want to be able to test ideas quickly.
Yeah, it's got to be easy to use. So looking at table 1 in the paper, it's clear they were aiming for something different with Bench, striking that balance between RL complexity, reasoning demands, and ease of setup. What were the key design choices that make it so unique?
They really focused on a few core principles. One, task complexity. For this, they focused on tasks that involve creating real-world artifacts, things like writing code and designing web pages. Tasks that require understanding structure, nuanced design choices. And they have to deal with collaborators who might not be perfect in unexpected scenarios, just like in the real world.
Makes sense. You want these agents to be prepared for anything.
Right. And then there's minimizing overhead. For this, they used a clever technique, reference artifacts. So by having a target solution, you can use LLMs as human simulators that have access to the ground truth. This means the simulators can give more realistic and context-aware responses to the agent's questions. It also allows for objective evaluation. You can measure how close the agent's output is to the ideal solution.
Oh, that's smart. So you have a clear measure of success.
Yeah, and the best part is it doesn't take a ton of resources to set up. You just need access to an LLM API and some basic Python packages. And of course, the final design principle is task diversity.
Right, making sure there's enough variety to keep things interesting.
Exactly. Here they use procedural generation to create over 10,000 unique tasks. And it's super easy to add more, just throw in more examples of code and web pages, and you get even more variety. The agents can't just memorize a few solutions, they have to really learn to generalize. Plus, the difficulty can be adjusted, which is crucial for studying how these algorithms scale.
So we've got this really well-designed, adaptable benchmark. What kind of tasks does it actually include? What are these agents doing in Bench?
They've got two main tasks. The first one is back-end programming.
Okay, so we're talking about writing code.
Yeah. So the agent has to collaborate with a human simulator, another LLM, actually to write a Python function. Usually it's less than 50 lines of code. They get a high-level description of what the function should do and the function's signature. But the tricky part is that key details about the implementation are missing. The agent has to ask the simulator for clarification, kind of like a programmer would ask a colleague.
Ah, so it's a real back and forth process.
Exactly. And they have a limit of 10 rounds of interaction. What's really cool is that the human simulator, this more capable LLM they used Llama-3.1-70B-instruct, has the reference code. But it won't just give it away. The agent has to ask specific questions, which forces it to think about what information it really needs. And at the end, the agent's code is tested with 10 hidden unit tests. It either passes or fails. It gets a 0 or a 1.
So it's not just about generating code, it's about engaging in a meaningful dialogue to get the job done. What's the second task?
The second one is front-end design.
So now we're moving to the visual side of things.
Yeah. This time, the agent collaborates to design a web page based on a high-level description. They represent the web page as an HTML snippet, around 100 lines of code. But again, the key visual details, like the layout, the colors, all that are missing, the agent has to work with the human simulator to figure those out.
Sounds challenging.
It is. The process is iterative. The agent writes some HTML, it gets rendered so they can see what it looks like, and then the human simulator, they use a vision language model like QN2VL72B for this, describes the visual differences between what the agent made and the reference design. They get 10 rounds of interaction. And the evaluation is a bit more nuanced here. They use clip embeddings to calculate the similarity between the agent's design and the reference. It gets a score between 0 and 1. For this one, they used data from the website dataset, and they used a mix of Llama and Q models to generate the initial training data.
So Coalbench sounds like a really robust and well thought out benchmark. Now let's dig into the algorithm they created, SWE-RL. The name itself kind of gives you a hint about what it's all about.
RL with stepwise evaluation from training time information.
Yeah, a mouthful, but informative. What's the big idea behind it? What problem are they trying to solve with SWE-RL?
The core innovation of SWE-RL is how it handles this really tricky problem called the credit assignment problem, which is a big challenge in multi-turn scenarios with LLM agents. Think about it. In a long conversation, it could be really hard to tell which actions led to the final outcome.
Yeah, if something goes wrong, how do you know where to place the blame or the credit for that matter?
Exactly. And that's where SWE-RL comes in. It uses information that's available during training, but that the agent doesn't see during the actual interaction. Things like the reference solution that we talked about at Coalbench, they use this training time information to train a critic, which basically gives the agent more informed feedback at each step.
Oh, so it's like the critic has a cheat sheet.
Yeah, kind of. And that's crucial because if you just rely on the final reward signal, especially if it's sparse like that 0 or 1 in the back-end programming task, the learning process can be super slow and inefficient. The agent is just stumbling around in the dark.
So the critic gets to see the answer, but the agent has to figure it out through conversation. How does this asymmetry actually make the training process better?
This is where the whole idea of an asymmetric actor-critic architecture comes in. You've got the agent, which is the actor that only sees the history of the dialogue. And then you have the critic, whose job is to evaluate how well the agent is doing. The critic, however, gets to see this extra information. By giving the critic this context, it can make a much better judgment about whether the agent's current action is actually helpful, whether it's moving towards the desired outcome.
It makes sense to give the critic more information. So instead of a value function, they're directly learning an advantage function. What's the advantage of that?
Well, the advantage function basically tells you how much better an action is compared to the average action in that situation. Instead of trying to figure that out indirectly from a value function, SWE-RL just learns it directly. They actually draw a parallel to preference optimization techniques in RLHF, reinforcement learning from human feedback.
Oh, interesting. That's where you have humans giving feedback to guide the learning process, right?
Right, so they train this advantage function using something called the Bradley-Terry objective, which is usually used to model pairwise preferences. But here, they've cleverly adapted it to train the LLM to prefer trajectories with better cumulative rewards. They have pairs of trajectories paths the agent could take, labeled as chosen or rejected, based on whether they led to success. The Bradley-Terry objective basically pushes the advantage function to give higher scores to actions that are part of those chosen trajectories.
So it's learning to distinguish between good and bad collaborative behaviors. How do they actually implement this advantage function within the LLM? It seems like that would be a pretty tricky part.
This is another really clever part of their approach. Instead of creating a whole new neural network just to predict the advantage, they use the LLM's existing language model head. It's very elegant. The advantage of an action is basically calculated as the ratio between the probability of that action under the train policy and the probability of the same action under a frozen reference model. This ratio is then normalized by the length of the response.
Okay, so they're not adding any new components. They're just cleverly using what's already there.
Exactly. And the beauty of it is that it stays closer to the LLM's original pre-training objective. That means it generalizes better and learns more efficiently from the fine-tuning data.
So once they have this trained advantage function, which is the critic, how do they use it to improve the agent's policy, the actor?
This is where the second stage of SWE-RL comes in. It's an asymmetric actor-critic approach. Critic, with its extra knowledge, acts as a guide for the actor. They use direct preference optimization, DPO, to fine-tune the actor's policy. In each turn, the algorithm samples a bunch of candidate actions from the current policy. The trained advantage function is then used to rank these candidates. Actions with higher advantage scores are labeled as chosen, and the ones with lower scores are rejected. These pairs are then used to update the actor's policy using the DPO loss.
So the critic is giving the actor feedback at every step, saying, do more of this, less of that.
Exactly. It's like having a coach whispering in your ear during a game, telling you what plays to make. There's a little practical detail here. They sample 16 candidate actions and use the top and bottom 50% to create these preferred and dispreferred examples for the policy update.
So we've got this sophisticated way of training these agents. How well did it actually work? What were the results when they tested SWE-RL on Bench?
The results on Bench were really promising. They found that SWE-RL significantly outperformed other state-of-the-art multi-turn RL algorithms. They saw a 6% absolute improvement in both the task success rate and the win rate, which is a substantial margin in this field.
That's a pretty big leap. So what does that mean in terms of practical performance?
Well, one of the most interesting things they found was that even a smaller model, Llama-3.1-8b, when trained with SWE-RL, was able to match or even beat much larger proprietary models like GPT-4o on these complex tasks.
That's really impressive. So you're saying a better algorithm can actually overcome limitations in model size?
Exactly. It's not just about brute force, it's about cleverness. They also compared SWE-RL to other RL methods like rejection fine-tuning and multi-turn DPO. They found that rejection fine-tuning tended to overfit and didn't generalize well. Multi-turn DPO struggled with assigning credit over long sequences of actions. SWE-RL consistently came out on top, which shows the effectiveness of this turn-level credit assignment with the help of that well-informed critic.
It's always good to see a new approach beating out the old ones. They also did ablation studies, right, where they remove parts of the algorithm to see how important they are. What did those tell us about SWE-RL?
Yeah, the ablation studies are super important because they help you understand what's really driving the performance. One of the biggest findings was that using the training time information was crucial. When they took that away, the performance dropped significantly. So having a critic that knows what it's talking about makes a big difference. They also tried using a regular LLM as a judge of actions, and that didn't work as well. It seems like these models can get distracted by surface-level features and miss the bigger picture. Another interesting finding was that using a traditional value function instead of their advantage function approach led to worse scaling with more data. That highlights the novelty of their approach.
So they were right to go with the advantage function.
Yeah, and they also found that normalizing the advantage function by the length of the response was crucial. Otherwise, the actor would start generating really short, unhelpful responses.
Oh, so it was trying to game the system by just saying as little as possible.
Exactly. They had to make sure it was incentivized to give informative answers. And then they looked at how SWE-RL scaled with more training data. They found that it might need a bit more data initially to train the critic, but then it quickly catches up and surpasses the other methods as the dataset grows. That means it's better at utilizing large amounts of data to learn those really robust and generalizable collaborative strategies.
So it's a bit more data hungry at first, but it pays off in the long run. They even tested SWE-RL with a much larger base model, the Llama 3.170b instruct, using data generated by the smaller 8b model. What was the point of that?
They wanted to see how well it worked with off-policy data, data that wasn't generated by the model being trained. It's a tougher challenge. They found that rejection fine-tuning really struggled in this setting. It basically just copied the mistakes of the smaller model. Multi-turn DPO did a bit better, but SWE-RL still showed a similar improvement over the baselines. That suggests that the credit assignment strategy in SWE-RL is pretty robust. It can learn from data generated by a different model.
That's really cool. So to sum up, what are the core innovations that make SWE-RL so special? What are the big takeaways?
I'd say the main innovations are in how they tackled the credit assignment problem. They've got this asymmetric actor-critic setup where the critic has this privileged information. They directly learn an advantage function using the Bradley-Terry objective, which is a clever way to model preferences for actions. And they parameterize the advantage function using the existing language model head, which improves generalization and keeps things efficient.
And we can't forget about Bench. It sounds like a really valuable tool for researchers studying multi-agent RL.
Absolutely. It's a brand new benchmark that fills a real gap in the field. It's challenging, it's diverse, and it's easy to use. A great platform for future research.
So, taking a step back, what are the implications of this research? What does it mean for the future of AI?
Well, I think it really pushes the boundaries of what we can do with AI. It gets us closer to having AI systems that can truly collaborate with humans, that can reason and strategize together to solve complex problems. The success of SWE-RL in these content creation tasks shows that AI can be a powerful tool for creativity and productivity, but it also highlights the importance of designing these algorithms carefully. We need to make sure they are reliable and effective partners.
It sounds like SWE-RL is a big step forward, but it's just the beginning, right? There's still a lot more to explore.
Oh, definitely. It's a promising foundation, but there are many open questions and avenues for future research.
Okay, so for our listeners who are really interested in the nitty-gritty details, definitely check out the paper. It's ARCS-XIV.2503.15478V1. And there's also the code repository and the Bench dataset on Hugging Face. You can play around with it yourself and see how it all works.
I think the main takeaway here is that we're still in the early days of collaborative AI. We're just starting to unlock the potential of these systems. SWE-RL is a great example of the kind of innovation that's happening, and I'm excited to see where this field goes next.
It's really an exciting time to be following this research. It makes you wonder if we can train AI to be better collaborators, how will that change the way we work, the way we create, the way we interact with technology in general?
Exactly, and that's the question I'll leave you with. What kind of future do we want to build with these increasingly powerful and collaborative AI systems? What role do we want them to play in our lives?
Lots to think about. Thanks for joining our deep dive today.
My pleasure.